ask an amateur how to solve a complex computational problem, and they'll almost always do the exact same thing: open a code editor and start typing. It's the digital equivalent of a contractor who walks onto an empty lot and immediately starts laying bricks. Bypassing the planning phase leads to cascading logic failures and scope creep. Without a blueprint, syntax quickly becomes unmanageable and prone to collapse. Professional software engineers avoid this trap by adhering to a strict, non-negotiable methodology, the Program Development Lifecycle, or PDLC. The PDLC is a deterministic protocol. It forces developers to map the entire logical architecture of the system long before a single character of actual code is written. It consists of 4 strictly sequential stages: analysis, design, coding, and testing. From banking networks to smartphone apps, reliable computer systems are the product of mathematical and structural engineering. The first boundary we have to clear is analysis. This is the foundation of software engineering. You start with a messy, real-world problem and apply abstraction. The goal here is to strip away the irrelevant details and gather the precise initial requirements. To do this, developers must isolate 4 highly specific data parameters: the inputs the system will receive, the processes it will run, the outputs it will generate, and the exact storage requirements needed to hold the data. This is a strict imperative. You have to lock down every single one of these system boundaries before moving forward. If you fail to clearly define these constraints, you will end up building a solution to the wrong problem. The subsequent code becomes useless regardless of its quality. Analysis takes a vague client request and forces it into a rigid, solvable mathematical constraint. Once the constraints are locked, we move to the design phase. This is where those abstract rules are turned into a concrete logical architecture. The primary method for tackling a complex, monolithic software problem is called top-down design. To execute a top-down design, engineers use a specific technique known as stepwise refinement. Stepwise refinement is a recursive process. You take the large, intimidating system and systematically break it down into smaller, highly manageable subsystems. You cannot stop dividing simply because the problem looks easier. The strict end condition for this process is that you must continue splitting the subsystems until every single node performs exactly one specific action. To visually map this hierarchical breakdown, engineers use a standard tool called a structure diagram. At the absolute top level sits your overarching system, an alarm app for a smartphone. The first level of refinement divides that main app into its core subsystems: setting the alarm, checking the time, and sounding the alarm. Some of these Tier 1 blocks might be simple enough to code right away, but others, like the sound alarm module, contain multiple steps and are still too complex. So we split it again into singular executable actions: playing a sound for 2 minutes, checking off a snooze button, and resetting the alarm. Once you hit those single action nodes, you can map the internal logic of each specific block using flowcharts and pseudocode. By forcing this continuous division, stepwise refinement guarantees that no single part of a program is ever too complex for a developer to confidently solve. With the logic fully mapped, we advance to the third stage, coding. Programming translates the logical architecture into machine-readable syntax, such as Python or Java. When coding begins, it always targets the lowest level nodes of your structure diagram first. By building these isolated modules independently, you guarantee that working on the snooze function won't accidentally break the clock logic elsewhere in the system. This phase is a controlled, deliberate process. It requires continuous, iterative testing of each individual module as it is drafted. A robust design phase provides the logic against which the code is tested, making it easier to distinguish between implementation errors and structural flaws. The actual typing of the code is the physical assembly of a system that you have already proven works on paper. Finally, the assembled modules are passed into the last pipeline stage, testing. Testing is a rigorous verification process. This is where you check the completed system against the analytical constraints established in Phase 1. You cannot rely on random keystrokes to verify the software. Engineers must construct a highly specific set of test data. The first required category in that set is normal data. Normal data consists of standard inputs that the program processes perfectly to yield a predictable result. If you have an algorithm designed to average student exam percentages, Feeding it a standard score of 50 should yield an expected output of exactly 50. Processing a standard number is easy. A system's true resilience is proven by how it handles the second data category, erroneous or abnormal data. Erroneous data comprises logically invalid inputs that the system must safely and intentionally reject without crashing. If the algorithm encounters a negative score, like -12, or a text string, like the word 11, recognizing and refusing those values prevents a database failure. A fully engineered system is defined by what it correctly processes and what it successfully rejects. The program development lifecycle enforces a strict progression. Analysis defines constraints, design decomposes logic, coding translates syntax, and testing verifies execution. When a severe bug appears during final testing, it is rarely a simple typo. It is almost always a symptom of poor analysis or a rushed design. Adhering to the PDLC removes the guesswork, the scope creep, and the panic from programming. Replacing the instinct to immediately type code with the discipline of stepwise refinement is the exact moment you transition from programmer to software engineer. To master the architecture of computation, head over to studybuddy.tech. There, you'll find advanced modules on system decomposition, software frameworks, and the engineering methodologies that build the modern web.